Hello everyone, it's August 5th. Alright, let's do this. Fruit into basket, number 3. 2 arrays of integers. I think that's exactly the same, but with a much larger. Place the fruit according to the rule. Each fruit type must be placed in the leftmost available basket with a capacity greater than or equal to. Each basket can hold only one type of fruit. If a fruit that cannot be placed, it remains unplaced. The number of... That's exactly the same as yesterday, but we have a much bigger, which means O(n) squared does not work. But yesterday we didn't think of another method, so might as well just go right into the hint. Sort the baskets by the pairs. Okay, so by doing this, we know the position. Alright, let's say we sorted. Then what? Right, let's say we sorted. So this will be 3, 0. 4, 2, and 5, 1. So when 4 comes in, I can binary search to know what is the smallest that... So like from this towards the end, they will all serve this. But what I want to know is what's the smallest index, right? What's the smallest index? So the smallest index so it's like a suffix min. From this toward the end, what's the smallest index? And then I say, okay, the smallest index is 1. Then I grab it. But how do I update this suffix min? Because I used it, right? So what's the second smallest? Yeah, basically just which one we want to know the smallest among them, and then once we're done with it, we need to remove it. Okay. For each fruit from left to right, use binary search to find the first index in the sorted such that basket I is larger or equal to fruit. Yes, I can do that. In 3, use a segment tree. A segment tree to maintain the smallest original indices. So, a segment tree to find the min among this. What's the final one? Mark it as used, will set it to infinite. I think I can set the index to infinite, right? So then, alright, so we need to use segment tree. I am not doing segment tree. Is this segment tree? Jesus, square root decomposition. What the hell? Alright, this is the one. Let's just see how they build a segment tree. So, segment tree... Why this? I think it's the number of segment tree. Should be 2 to the n. Huh. Why you set this value segment tree? It's the value. Wait, hold on. I thought segment tree here is to get the max. This is a template problem for a segment tree. To maintain the maximum value of the baskets array over what? Maximum value of basket array. Oh, wait a second. Wait, hold on. That's different from the hint. And then use binary search to find the first basket that meets the condition. Establish a tree where the content maintain initialization is the maximum value of each interval. Okay, so they're doing max. They enumerate fruits and they use a segment tree to find the maximum value in the interval during the binary search. Oh, I see. It's different. It's binary search procedure, which means they will do the first half and second half and find a max, right? If the max is on the first half, and they go there and then they keep doing, and then use that to find the leftmost that's good. It's different. Yep, set the value to 0. Yep. Yep, if the max value is in the left is less than down, and the max on the right is greater, continue the binary search in the right one. Otherwise, there is no interval that meets the yeah, this one will work. It will work. So we maintain the max. This is build, query, and update. Build. Oh, segment tree. Jesus, I don't quite remember segment tree. Screw me. So this basket size. So we build. So what the hell is P? What the hell is R? There's a left and right. And to build a segment tree. How do you build a segment tree? So let's put the value. LR is indices, right? L and R is indices of LR is indices of the thing. P is the index on the segment tree. How did you come with 4? I think I used to know what's I think it's like how many layers, right? So it could be log n, log 2n, right? And then number of layers, then there's 2 to this plus 1. I think it's this. So we have the layers is gonna be log 2n, and then the segment tree is a complete tree. So if you have 2 layers, you have 3 layers. Right, so 2 layers is 2 to the 2 minus 1. 3 layers is 2 to the 3 minus 1. So I have this layer, so it should be 2 to the layers. And this shall be a ceiling minus 1. So we can actually compute to see if our understanding is correct. Right? So it's basically log 2 10,000, right? So that's 16. So take the ceiling is going to be basically a 17, right? So we're going to say 2 to the 17 minus 1. That is absolutely wrong. Yeah, that's not right. But there is going to be 17 layers. Right? 17 layers. Oh, wait, hold on. This is not right. This is the last one. The last one. Last row has n. Right, last one is n. And we need to make it, right? Make it into, so it's 2 to the 17. The last row, okay? The last row should be 2 to the 17. And then we need to find, so basically it's 2 to the 0 plus 2 to the 1 plus all the way to 2 to the 17. What's this? This is 2 to the, oh my god. (18 minus 1, I think. Yeah, I think it's 2 to the 18 minus 1. That is still not right. What the hell? Huh? Constraint. Yeah, it's 10 to the 5. Right? It's 10 to the 5. There's the position. The basket position is 10 to the 5 at the bottom layer. And 10 to the 5 is about 16. So I do 17. It's at the bottom. I don't understand. That I do not understand. Why is this full? Actually, this is even bigger. This is 400,000, so not 40,000. Huh? Yo, this is very different from what I had.
Oh.
I don't know why it's that big. Anyway, if it's the same, yes. And then we have a mid, yes. So build. So yeah, so if it's a 0, it'll be 1 and 2, 3, 4, 5, 6. So the left will always be 1 times 2 plus 1. The right will be 1 times 2 plus 2. So that's the left and right. And then the left and mid plus 1, yes. Segment tree will be the maximum of the left and right, yes. I got this one. This is the build. Query, query. So we have query left, query right, yes. And then left and right, yes. So if query left is larger than the right, or query right is smaller than L, then that's impossible. If query left is smaller equal to left, and the query right is larger equal to R, so the query covers the current, so we return the current. That is okay. So the third is the query left is larger than L and the query right is smaller than R, right? So we're landing in between. Then you split in the middle, and then you do left to mid, and a query left, and a query right. Oh, wait, hold a second. The query left, query right never changes? That's odd. I would change query left to query right, but I guess this is a better way. Because if you don't change query left to query right, then you don't have to think too much, and you can use this. Okay, so this is get a max, update the position. If it's the same, you do this. If you got a mid, if the position is smaller than mid, then we update the left half, otherwise we'll update the right half. And then we have to update this. Oh my goodness. And then this is the boundary search for each one. You will go, yes, you get a middle, and then we'll query the left half. If it's larger than this, you will say res equal to mid. What's the point of this? The point of this is to find out if we can find one and update it, right? We want to find the actual basket. Yeah, res equal to mid, r equal to mid minus 1, yes, we continue. And then when we're done, if res is not equal to -1, so which means we find one, and this is actually larger than, then we will, what do we count? Unplaced, right? We count unplaced. So we'll update it, yes, and otherwise we count. Oh, segment tree. All right, I actually want to implement this. Why I just don't understand why it's set it at 400,000. Oh, is this the maximum we can set? Maybe why we cannot set at this value? I don't think we can get more than this. 262,000. I'm about half. Did they do 19? No? I don't understand. This is what I understand, unless I compute it wrong. Like the bottom layer needs to be this, right? So, yeah, okay. A to the 0 plus A to the 1 plus to A to the n. Right, so we set this to S. So AS minus A times S minus A shall equal to A to the n plus 1 minus 1. So A shall equal to A to the n plus 1 minus 1 divided by, not A, S minus S, my bad. A minus 1, right? So this is what we have. So it should be 2 to the 18 minus 1 divided by 1. Yeah, it should be 2 to the 18 minus 1. I am going to try, but not using this method, but using the hints. Well, the hint, they just slightly differently, right? We just slightly differently. We sort this. We sort the baskets, right? We sort the baskets so it has from small to large on the fruit, and then we will binary search that so we get the so we sort, then we get sort of the baskets out. Yes, sort the baskets out. Binary search it so we know which one is the smallest. And then what we want is in this range, which is the smallest index. Right? Which is the smallest index. Let's give this a shot. Oh, but it feels kind of late. I think it's gonna take a while. This is what I'm afraid of. But I have some help. Okay? I have some help. 3, 4, 7, 9. Hint and help from editorial. We'll follow the hint exactly. First, we sort baskets, but also get the indices. Then we use a min segment tree to get the min index, right? To keep track of the min index. Keep track of the min index for all segments. Then for each fruit from left to right, we binary search the sorted baskets to find the range. To find the range of baskets that have sufficient capacity, enough capacity. Then we use the segment tree to find the main index among these baskets. Right. And once the basket is used, we set its index to infinity. Right, we set its index infinity. We set its index to infinity. Okay. And how about its value? Because binary search will still get there. Oh, shoot. Yeah, binary search will still get there. Damn it. Oh, actually, hint is not good. The hint is not good. Yeah, like you binary search again, but you can't. You cannot binary search it again. Because if you binary search, you'll land on the same thing. But you cannot land on the same thing. So what would be an impossible case? An impossible case is, you know, there's no available that has the capacity, right? So okay, there may be something we can do. Yep, I don't think the hint will work. I don't think the hint will work. I don't think the solution from the hint will work. The hint says we first sort basket, then we use argument tree to find. Once value is used, we set its index. However, the problem, right? The problem is that the used basket is still in the sorted basket array, right? It's still in the sorted basket array. There's no way, there is no fast way to remove it from consideration during the next round of binary search. Right, next round binary search. So this will still, this won't work. The actual solution does it the other way around. It uses a max segment tree to find, the max basket in any given range. Then we binary search the baskets, right? If the max on the left half is already bigger than the fruit, we use it. Yeah, we continue search this half, right? Once a basket is used, we set its capacity to 0. Alright, we set its capacity to 0. So it will not be used again. Right, so it will not be used again during the subsequent rounds of segment tree query. Yeah, I think this is the only way that works. All right, let's see if we can get a segment tree set up. All right, so what do we need? We need a tree. So private vector seg tree. I think I'm gonna just try this. A whole 2.6. So I go 270,000. This is what I believe. Okay, this is what I believe. So I need a segment tree. What else do I need? I don't need anything else. Maybe I need basket. Why do I need basket? I can pass basket. Oh shit. I can't. How does it initialize? Oh my god. Alright, how do I initialize the size? Oh, I guess you don't. Reserve, right? 27,000. 270,000. Okay. Alright, then we have some functions to write. So build, yep. I would just follow. This is a segment tree, and then we have a left and we have a right. And we have a, alright, so I see your point. Vector int basket. You know what? I don't like it. I will just do it here. std vector int baskets. Okay, so now we're gonna build it. How do we build it? If L is equal to R, then we say seg tree P or equal to baskets L. Else, right, else, then we have a range, then we're going to get a middle. So mid is equal to L plus right minus left divided by 2. I think this is a safe way to do. And then we have the mid, then we can build. Oh, and also we need is a left P. So you go to P times 2 plus 1 and a right P. Alright, PL and a P left and P right. P left and then P right is P times 2 plus 2. So we'll build a P left, left and mid baskets. And then we'll build P right, mid plus 1, right baskets. Once we're done, we say seg tree P shall equal to maximum seg tree P left, seg tree P right. Alright, that is build, but why do you return? I will return, no, you don't need to return anything. I think this should be void. Alright, so that's that. And then we have void again. We will, no, actually, we'll need query. So query, what we need is left right, and then range left, range right. Oh, query left and query right. Okay, query right. I don't need anything else except I think I also need P. Right. So we say if left is large, if query left, okay, is larger than right, or query right is smaller than left. So in this scenario, we don't get anything. So we'll return, because it's the max, so we will just return the minimum. So int minimum. And if query left is smaller or equal to left, and query right is larger or equal to R, so we cover, so I'll return sec3 p. Okay. Otherwise, it's kind of contained inside. Then we need a mid is L plus R minus L divided by 2. It's the same thing. And PL is P times 2 plus 1. PR is P times 2 plus 2. Okay. And then what we're gonna do is we will return the maximum from both sides. So we have query PL, we'll do left mid QL QR, and this is query PR mid plus 1 right QL QR. Oh, this is much simpler than what I used to do in the past. Void update. So we have P, we have L, we have R, we have value. Right, let's just update a value. So again, if L is equal to R, then we just say sec3 P is equal to the val, else R minus L divided by 2, right? So we say if, actually that's not right. We need a position and we need, we have a value and we have, index. Right. So now is if index smaller or equal to mid, the left half, then we will update. Let me copy and paste this one again. It's good to just keep the same format. PLL mid index val, right? Else update PR mid plus 1 R index and val. Index. Yeah, because I have this index, I need to update the value to this. So we update, and then we update, and then once we finish update, right? Once we finish update, then sec3 P to maximum sec3 PL and sec3 PR. All right, that's the three functions. So we have this, we got a sec3, and then we'll call build. P in the star is 0. L, we need to also n equal to basket size. Alright. So will be 0. This will be n minus 1.
Oh.
Okay, so we build. And then we have rest should be equal to 0. we have to go through fruit one by one. So for int f of fruits, right? So I go fruit one by one, and for each fruit, I need a low, high, and index. So while low is smaller than high, right, mid is low plus high minus low divided by 2, right? So we got a mid. Then what? Then we need to find the max on the left half. So basically we say if query, no, we start with 0, oh Jesus. Query, so we start always 0, 0 and minus 1, and then we need a query left and a query right. Okay, so a query left and query right. So what is query left? Query left is going to be 0, query right is going to be mid. So if this value is larger or equal to f, okay, then we'll do something. What do we do? So it's on the left hand side. Then we say index shall equal to mid, and it's on the left hand side, so high shall equal to mid, right? High equal to mid, I shrink it, and mid is, what are we doing here? We are, index essentially means, yeah, index should be -1. Index is what index? What basket, right? What basket did we find? What basket did we find? I mean, essentially, at the end, you will be the one that we find. So actually, we don't even need this, right? We don't even need this. Why do we need this? It's just like, this is gonna be high. And else, if query 0, 0, and minus 1, right, from mid plus 1 to n minus 1, nope, 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 this is not right, this should be low, this should be high. So we find the maximum if this is larger equal to fruit, right? Then we should search on the right hand side, which means low should be mid plus 1. And there's one more else, right? This else is not possible. Okay, it's not possible. Then we shall just break it. Right, we should just break it. I see what you're doing here. Yeah, I guess it's fine. Because at the end, the low needs to equal to high. So if the low is not equal to high, right? If low is not equal to high, then you break out. That means we just like we given the current range, we do left, and we do left to fail, and then we try right also fail, right? Otherwise, we'll do left. If it fail, then we try right. So I'd say in this case, we just simply break it out. Okay. So blah blah blah. Once it's done, we're gonna check. We say if low is equal to high, right? that means we have found it. We have found the index, right, that allow us, because high equal to mid is not going to work, and we high equal to mid, and we try it again. Well, we try it again if low is, it's only when low equals to mid plus 1. Like, this is good. Yeah, if the left half is good, so I move here, and then the left half is not good, but the right half is good, so I move it here. Left half is good, but I don't move right half is good. Yep, so if they're the same, that means we've found it. Then what we need to do is what is set its value to negative infinity. Doesn't even have to be negative infinity. We just set it to, we can just say baskets low -1, and then update. So update is plr index file. P L R index val. Else means this position doesn't have any, so I will go plus plus. Now return rest. Alright, so this is completely oh, but reserve doesn't really do, right? Alright, how to fill reserve vector and fill it with 0. You have fill reserve oh, wait, hold on. Maybe I can do it here. Can we do it here? I think we cannot. Yeah, it cannot, because this is just to define it. Alright, so I'll reserve, and then I will resize. Alright. Let's hope this one is right. We had guidance, so let's see. Let's see if it's right. Pretty much is an edge case. I don't understand. So this is equal. Oh, basket low is larger than if. Yep. What the hell? Larger equal to. Oh, jeez. My man. You're killing me. My man, you're killing me. You're killing me left and right. Not bad. Not bad. I mean, we did read the solution, so we know where we're going, but hey, every time that I do segment tree, I always feel good. If segment tree is like this, it's actually not that hard, right? It's actually not that hard. I think the improvement in particular is the query. This setup for the query is actually very good. You have very clear condition when it's an impossible case, we always know that, and the possible case. And the key is once you do the possible case like this, you can maintain the same. Because I remember in my previous attempts at segment tree, I changed the query left. Like the query left and query right, I'll change. In this case, I'll actually make the query right equal to mid, and then this one has to change. So you have like multiple places you need to change, which is not advisable, right? Which is not advisable. Other than that, I mean, like, yeah, it's not that bad. It is not that bad, and the segment tree size doesn't have to be that big. I think my understanding of it is also correct. In fact, we can do even better, I think. So if I do this, so this will be, watch me, log 2 n, okay, so I'll cast into int. Doesn't matter, I just plus 1. Oh, wait, hold a second. Maybe they have ceiling. Yes, they do have ceiling. Alright, then I don't need to do this. And then I do need to do this, my bad. So this is the on the bottom layer, right? So in the plus 1, and then we need to do power, which is essentially just one left shift, right? So with one left shift this, and then minus 1. I just don't do minus 1, and I do this one. Holy crap! I'm not sure. Alright, I think you might be able to help us get the memory usage a little bit, maybe a bit lower. Okay, let's see. Will we be able to get the memory usage a bit lower? Yes! Not only do we get the memory usage lower, but we also get the runtime faster than before. All because I'm more judicious in the usage of the size, the segment tree size. See, it's not that bad, right? It's not that bad. I was a little bit reluctant actually earlier. I don't want to do this. I want to just read and then, yeah, this is a good question. I mean, from time to time you have to do segment tree, right? You just have to do segment tree. All right.